Hello, my name is David Brown. I'm an Associate Director at the Steel Construction Institute, and this presentation covers the demonstration of an extensive range of numerical worked examples, all in accordance with the Eurocode. So we'll classify, we'll check cross-sectional resistance, we'll verify buckling resistance, and then we'll finally consider columns in simple construction. So the classification process is important because both the cross-sectional resistance and the buckling resistance depend on the section classification. So for things in compression, are we going to use the gross area or the effective area? For things in bending, are we going to use the plastic modulus, the elastic modulus, or some other modulus? There are three sheets given in BSEN 1993-1-1. Sheet 1 covers internal parts, and for that we would recognise them as webs. Sheet 2 covers outstand parts, and we would recognise those as flanges, and Sheet 3 covers angles and hollow sections. For a rolled section, we would need to classify both the web and the flange, and we are going to compare the actual geometry with the limits given in the tables. The class of the complete section is taken as the most onerous classification from either the flange or the web. The limits generally depend on epsilon, and epsilon is related to the grade of steel, but along the bottom of the table on each one of those sheets we have the values of epsilon for the various different yield strengths of steel. So here is a typical example, this time for webs of rolled sections. We have a number of limits. It depends whether the section is in pure bending, in compression, or subject both to bending and compression. And the limits are given to us in terms of C over T. C is the depth between fillets, and in this case T is the thickness of the web. When webs are subject both to bending and compression, then we need to calculate alpha if we are considering class 1 or class 2, or if we are considering class 3, psi. The Eurocode doesn't identify how we should calculate alpha or psi, but if we draw the relevant stress blocks, so here is a plastic stress distribution, and we rearrange the expression which governs that stress distribution, then out pops an expression for alpha. And we can do a very similar thing if we have an elastic stress distribution and determine an expression for psi. This is the sheet that covers outstand elements, so this is flanges, and if a member is in major axis bending, or if it's in uniform compression, then the flange is going to be in uniform compression. And again, we just have a number of limits. C is from the root radius out to the tip of the flange, and T in this case is the thickness of the flange. So, if we are to classify a member under axial compression, we know from the code that class 1, class 2 and class 3 all use the gross area. If we find ourselves in class 4, then we use the effective area. So the real question is, when we classify under compression, are we at least class 3? Because then we know that we will be using the gross area A. So our first numerical example, it's a 305 UC97. It's in S275 material, and from the bottom of the table, epsilon for this grade of steel is 0.92. So first of all, we'll classify the web, and the C over T ratio from section property tables for the web is 24.9. The class 3 limit for a web in compression is 42 epsilon. 42 epsilon is 38.6. Our actual ratio is 24.9, so the web is at least class 3. We don't really mind if it's class 2 or class 1. All we need to know is that it's at least class 3, and therefore we will use the gross area. Considering the flange, the C over T ratio for the flange is 8.6. From the Eurocode, the class 3 limit for the flange is 14 epsilon. 14 epsilon is 12.8, our actual is 8.6, so the flange is also class 3. Because the flange is at least class 3 and the web is at least class 3, then the whole section is at least class 3, and we know with confidence then that we should be using the gross area. When we calculate the cross-sectional resistance, we need to know the classification, because we need to know whether we're using the gross area or the effective area, and we need to know which modulus we're going to use. We also need a design strength, and we need a partial factor. The UK National Annex says that the design strength must be taken from the product standard. So for convenience, here is an extract from the concise guide, which shows the design strengths for various material thicknesses and the ultimate strength. So for example, for S275 material, if the thickness is no greater than 16 millimeters, the design strength is 275 newtons per square millimeter. And for that very same material, the ultimate strength is 410 newtons per square millimeter. The partial factors are taken from the UK National Annex. So for cross-sectional resistance, which is the subject we're interested in for the moment, gamma m0 is taken as 1. Later, when we come to examples covering buckling resistance, we'll need gamma m1, and that's 1. And when we look at the resistance of something in tension, when we consider the net area check, when we use the ultimate material strength, then we will be dividing by the partial factor gamma m2, and that's given in the UK National Annex here as 1.1. So, to continue our example, the cross-sectional resistance in compression is the area multiplied by the strength divided by gamma m0. We would choose the area from section property tables, and then we can calculate the resistance as area multiplied by yield divided by gamma m0, which in this case 3,383 kilonewtons. An alternative and quick way to establish the cross-sectional resistance is to use lookup tables. So here is a lookup table from the Blue Book. We identify our section, a 305, 305, 97 UKC, and the cross-sectional resistance is given us as 3380 kilonewtons. So a little bit of rounding, but exactly the same figure. When we consider the cross-sectional resistance of elements in tension, there are two checks that we need to do. First of all, we need to calculate the resistance of the gross cross-section, and for that we would use the yield strength and gamma m0. And secondly, we need to calculate the resistance of the net cross-section using the ultimate strength and gamma m2. A typical example then might be a flat bar in tension. And in this particular flat bar, we have two holes for an M20 bolt. So the holes are 22 millimeters in diameter. The first check then is of the gross cross-section. So we calculate the gross cross-sectional area, and the resistance then is the area multiplied by the yield strength. But because the plate is 20 millimeters thick, which is greater than 16 millimeters thick, we take the reduced strength of 265 newtons per square millimeter divided by gamma m0, and the resistance is 1060 kilonewtons. The second check is of the net area, so we calculate the net area by removing two bolt holes, and then we calculate the resistance. Notice the 0.9 factor, 0.9 times the net area multiplied in this case by the ultimate strength, which is 410 newtons per square millimeter, divided by gamma m2, which is 1.1, and the answer is 1047 kilonewtons. So we then establish the minimum. It happens to come in this case from the net area, so the minimum resistance for this element is 1047 kilonewtons. Many people, of course, don't do both checks. They simply take the net area and use yield, which is okay, but notice that it's very conservative, because using the net area and the reduced yield strength results in a resistance of only 833 kilonewtons. Moving on then to the bending resistance of a restrained beam. Again, we need to classify, then we can check the cross-sectional resistance in bending. That may be reduced because of the effect of shear, so that needs to be checked, and then we need to calculate the deflection. Here then is a numerical example. It's a beam which is 6 meters long at 4 meter centers. We have some permanent actions, 3.5 kilonewtons per square meter, and an imposed floor load of 5 kilonewtons per square meter. Using expression 610, we can calculate the ultimate load, so 1.35 times the permanent actions plus 1.5 times the imposed floor load, and the ultimate load then is 48.9 kilonewtons per meter. We can then calculate the maximum bending moment, WL squared over 8, because the beam is simply supported, and the answer is 220 kilonewton meters. And we can also calculate the maximum shear force, which is at the end of the beam, and that is 147 kilonewtons. To choose an initial size, we need to select our steel grade. So in this example, we're assuming we have S355 steel, and we're going to assume that the beam is class 1. We may well know that every universal beam in pure bending is class 1, but we'll check that later on. So the bending resistance from the Eurocode, because we have a class 1 beam, is the plastic modulus multiplied by yield divided by gamma m naught. We can rearrange that expression to say that given the bending moment, if we take the bending moment and divide by yield, then we will find out the minimum plastic modulus that we require. And in this case, the minimum plastic modulus is 620 cubic centimeters. So from a table of section properties, we're interested in the plastic modulus. In the major axis, we're looking for a plastic modulus which exceeds 620. So it would appear that a 305 by 165 by 40 universal beam is appropriate. We do know that all universal beams are class 1 under pure bending, but if we wish to classify, again, we need to take the ratios for local buckling. So for the flange 6.92 and for the web 44.2. We would check those against the appropriate limit. So in this case, we'll check against class 1 because we do expect the beam to be class 1. For the web, the limit is 72 epsilon, and epsilon is given down at the bottom of the table for S355 steel as 0.81. So 72 epsilon is 58. The actual C over T ratio is 44, so as expected, the web is class 1. If we do the same thing for the flange, the class 1 limit is 9 epsilon. 9 epsilon is 7.3, the actual is 6.9, so the flange is class 1. So both the web and the flange is class 1, so as expected, the whole section is class 1. The shear resistance is given by the Eurocode as the shear area multiplied by yield divided by √3 divided by gamma m naught. The Eurocode defines the shear area, and here it is, so we simply substitute dimensions from section property tables and calculate the shear area as 2007 square millimeters. We can then calculate the shear resistance, and the result is 411 kilonewtons. So, straightforward stuff. The actual shear is only 147 kilonewtons, less than 411, so okay. We may need to concern ourselves about the impact of shear, because high shear reduces the moment resistance. But in this case, the high shear, which is at the end of the beam, is not coincident with the high moment, which is of course at mid-span. And in any case, high shear only has an impact when the applied shear is more than 50% of the shear resistance. In this case, the applied shear is nowhere near 50% of the shear resistance, so we wouldn't have an issue with high shear even if they were coincident. We need to check out deflection. So the UK National Annex says that we should use the characteristic combination, but we should not include the permanent actions. So in this case, we're just going to check the deflections using the variable action, which is for us the imposed floor load. So the imposed floor load is calculated as 20 kilonewtons per metre, and that results in a deflection of 18.9 millimetres. We look in the National Annex for the deflection limits. It depends on the type of beam. In this case, we will take the more onerous limit of span divided by 360. We calculate the limit. The answer is 16.6 millimetres. Our actual is 18.9 millimetres. So in fact, if we are to use this more onerous limit, we would need a slightly stiffer beam. If we repeat that exercise, but now using lookup tables, we have a design moment of 220 kilonewton meters. We have a design shear of 147 kilonewtons. We could look at the member resistance tables, and for a 305 165 40 UKB, we see that the bending resistance is 221 kilonewton meters. A reminder there that we are a class 1 section, and the shear resistance is 411. Only the deflection remains to be calculated, and of course we would find the same thing, that we would need a slightly stiffer beam. Moving on then to buckling resistance. First of all, considering elements subject to axial compression. The axial resistance is a reduction factor chi multiplied by the area multiplied by yield divided by, this time, gamma m1, which again from the UK National Annex is 1.0. To calculate chi, we need to determine the non-dimensional slenderness. And in general, the non-dimensional slenderness is given by the root of the area multiplied by yield divided by the elastic critical buckling load, N crit. If we limit ourselves to flexural buckling only, then there is an alternative way of calculating lambda bar, and lambda bar then is equal to L over I, which is the buckling length divided by the radius of gyration divided by a constant lambda 1. So a numerical example then of a 203 UKC in S355 steel, and it's 6 meters long. The process that we're going to follow is first of all to classify, then we'll calculate the minor axis resistance, then we'll calculate the major axis resistance, and then we'll calculate the torsional resistance. So, first of all to classify. For our selected member, we have the ratios for local buckling for the flange 6.2 and for the web 17.1. For the web, the class 3 limit is 42 epsilon, which is 34. Our actual is only 17, so the web is certainly at least class 3. For the flange, the class 3 limit is 14 epsilon, which is 11.3. Our actual is only 6.2, so both flange and web are at least class 3. And at least class 3 is important because class 1, class 2 and class 3 all use the gross area. So the only test for axial compression is the member at least class 3? Then we need to select a buckling curve, so we would turn to the Eurocode. We have a rolled section. The H over B ratio, well, this is a universal column, 203 divided by 203, so the H over B ratio is less than 1.2. We then need to know the flange thickness, but it's certainly less than 100 millimeters. We're currently interested in the minor axis buckling, and therefore we would select curve C. Now we need to calculate the non-dimensional slenderness. There are two alternative methods. For now, we will calculate the non-dimensional slenderness by the buckling length divided by the radius of gyration divided by this constant lambda 1. We then need to select the radius of gyration. So for the minor axis, the radius of gyration is 5.2 centimeters. We can then calculate lambda bar. First of all, we need to calculate lambda 1. So lambda 1 is 93 epsilon. Epsilon is the root of 235 divided by the yield strength. So in this case, lambda 1 is 76.4. So lambda bar, therefore, is L over I divided by lambda 1, which results in a value of 1.51. Having calculated lambda bar and knowing the curve that we're concerned with, we can then use a table from the Eurocode to extract the reduction factor chi. So along the bottom of this particular table is lambda bar. Lambda bar we know is 1.51. We know that we're to use curve C, and therefore reading to the left, the reduction factor chi is 0.31. We can then calculate the resistance, chi times area times yield divided by gamma m1. The strength we should use depends on the material thickness. The flange is less than 16 millimeters, so therefore we will use 355 newtons per square millimeter. We pick up the gross area from section property tables and we calculate the resistance therefore as 841 kilonewtons. The alternative approach is to calculate the elastic critical buckling load, N-crit, which for flexural buckling is the Euler load, pi squared EI over L squared. So picking up I from section property tables, we calculate N-crit. We can therefore calculate lambda bar and we get exactly the same answer, 1.51. So we could use the same graph and get exactly the same answer, or alternatively, we could calculate the reduction factor from the expressions given in the Eurocode. We need to select the imperfection factor alpha, which relates to the curve. We already know that we're interested in curve C, so the imperfection factor is 0.49. So we know everything now to calculate phi. So substituting the things that we know, our value of phi is 1.96. Now we can calculate chi, and the value of chi is 0.31. So the resistance, as we calculated before, is 841 kilonewtons. Doing the same thing in the major axis, we need to select the curve. So it's still a rolled section. H over B is still less than 1.2, but now we are interested in the major axis, and therefore we identify curve B. We need the radius of gyration, this time in the major axis, so this is 8.96 centimeters. So we can calculate lambda bar again, L over I divided by lambda 1, in this case, is 0.875. And instead of calculating, or instead of using the graph, I'm now going to use a lookup table, which has been taken from the concise guide. So we know our value of lambda bar, 0.875. We know we're interested in curve B, so with a little bit of interpolation, we can calculate chi as 0.677. So in the major axis then, the resistance is chi multiplied by the area multiplied by yield divided by gamma m1, and that results in a resistance of 1836 kilonewtons. Moving on then to torsional buckling. The elastic critical buckling load for torsional buckling looks complicated, but most of these terms are just section properties. I0 squared is the sum of the squares of the radius of gyrations about the major and minor axes. Y0 and Z0 in a doubly symmetric section are both 0. So I0 squared, we've seen these values of 89.6 and 52 before, so I0 squared is 10732 square millimeters. Everything else is either a constant or is a value that we can pick up from section property tables, so we can calculate the elastic critical buckling load for torsional buckling. We can then calculate the non-dimensional slenderness, and we can't use the alternative expression in this case because the alternative expression is only appropriate for flexural buckling. So we must use the general expression, the root of area times yield divided by the elastic critical buckling load, and in this case the non-dimensional slenderness for torsional buckling is 0.766. At this point we have a number of options, because the Eurocode says when we're considering torsional buckling we use the curve for minor axis flexural buckling. Therefore we could use the figure given in the Eurocode, or we could calculate, or we could use a lookup table. First of all, I'm going to calculate, so we determine the value of phi, and then we can calculate chi as 0.683. Alternatively, we can use the lookup table. Curve C is appropriate for minor axis flexural buckling and therefore is also appropriate for torsional buckling. We know the value of lambda bar as 0.766 in this case, so with a bit of interpolation, the value of chi 0.683. So we can calculate the torsional buckling resistance as chi multiplied by area multiplied by yield divided by gamma m1, and the answer in this case 1854 kilonewtons. So the three calculations that we've just completed are for major, minor and torsional buckling. Of course, it's an awful lot easier to use a lookup table. So here is a lookup table from the blue book for our chosen section. Here is the buckling length highlighted as 6 meters, and here are the values from the blue book: 1830, 844 and 1850. So at some point in my calculation there have been some rounding issues, and that's why we don't get exactly the same as the blue book. You may wonder why we haven't checked torsional flexural buckling, and the answer is that a universal column section is symmetrical, and therefore torsional flexural buckling is not an issue. Moving on then to lateral torsional buckling, there are three methods available in the Eurocode. There are buckling curves, there is a simplified assessment method, and there is the so-called general method. For rolled sections, we will generally be using the buckling curves, and hopefully we will be using the curves which are appropriate for rolled sections, because we will get an increased resistance from those expressions. The lateral torsional buckling resistance is expressed as the reduction factor chi LT multiplied by a modulus multiplied by yield divided by gamma m1. The modulus depends on the classification. So for class 1 and class 2 sections we'd use the plastic modulus, for class 3 the elastic modulus, and so on. To determine chi LT we need the non-dimensional slenderness, and the non-dimensional slenderness, rather like the expression for flexural buckling, is defined as the root of the modulus, and again the modulus depends on the classification, multiplied by yield divided by m crit, the elastic critical bending moment. So numerical example, we have a universal beam, it's in S355 steel, it's 6 meters long, and it's subject to a UDL. The process is first of all to classify so that we know which modulus to use, then we can calculate m crit, then we can calculate the non-dimensional slenderness, we need to select an appropriate buckling curve, and then we can calculate the reduction factor chi LT. In truth, we know that all universal beams are in fact class 1. But if we were to classify from section property tables, we determine the ratios for local buckling. For the flange 5.03, for the web 41.2. According to the Eurocode, for the web the class 1 limit is 72 epsilon, which is 58. Our actual ratio is 41.2, so as expected the web is class 1. The limit for the flange is 9 epsilon, which is 7.3. Our actual ratio is 5.03. So, as expected, the flange is class 1. So with both the web and the flange as class 1, the whole section is class 1, and therefore we will use the plastic modulus. Then we must calculate the elastic critical buckling moment. The important feature here is the C1 factor, and the C1 factor allows for the shape of the bending moment diagram. The C1 factor is not given in the Eurocode, and therefore we need to turn to a source of NCCI to choose the C1 factor. So from the concise guide, here is a simply supported beam subject to a UDL. The C1 value in this case is 1.127. So 1.127 has been rounded up in this calculation to 1.13. All the other terms are either a constant, pi, or Young's modulus, or the shear modulus, or they're determined from section property tables, and MCRIT in this case has been calculated to be 387 kilonewton meters. Alternatively, we can use free software called LTB from CTICM. Here we've selected the appropriate beam, 457.191.82. It's got the correct length of 6 meters. We apply a uniformly distributed load because the shape of the bending moment diagram is absolutely critical. And the result is, according to the software, 388 kilonewton meters, whereas by calculation we had calculated 387 kilonewton meters. So again, there's some modest rounding differences between the two answers. Having calculated MCRIT, we can then calculate lambda bar LT. We know that we're to use the plastic modulus, so lambda bar LT is 1.3. We then need to choose a curve. We have 2 sets of curves available, the general case or a case specific for rolled sections, and I would commend that we use the case specific for rolled sections if we have a rolled section, because we will get a higher resistance. If we do choose the rolled section case, then we need to choose our curves from table 6.5, but that table has been modified by the UK National Annex. So here is the modified table from the UK National Annex. We know we have an I section. H over B is the section depth divided by the section breadth. So 457 divided by 191 is 2.39. It's greater than 2, but less than 3.1. So we select curve C. We can then choose the imperfection factor alpha LT. For curve C, alpha LT is 0.49. So, knowing alpha LT and knowing lambda bar LT, we can now calculate phi LT. There are 2 terms which are recommended in the Eurocode but may be adjusted by the UK National Annex. Those are lambda bar LT0 and beta, but the UK National Annex for rolled sections accepts the recommended values. So as we calculate phi LT, we'll use beta as 0.75 and lambda bar LT0 as 0.4. So substituting everything we know for phi LT, the value of phi LT is 1.35. We can then calculate chi LT. Again, we're going to use the recommended value for beta, and chi LT equals 0.48. If we've selected the curves which are appropriate for rolled sections, then we are allowed to determine a little more resistance by calculating a modified value of chi LT. And chi LT mod is equal to chi LT divided by F. F is given us in the Eurocode. F primarily depends on this term Kc, and Kc is associated with the shape of the bending moment diagram. From the UK National Annex, Kc is defined as 1 over root of C1. We know that for a UDL, C1 is 1.13, so in this case Kc is 0.94. We can then substitute everything we know for F, and we find that the value of F is 0.985, and we immediately realise that to divide something by 0.985 is hardly any benefit, because chi LT mod, instead of being 0.48 as chi LT, only increases very slightly to 0.49. So the lateral torsional buckling resistance is now chi LT mod multiplied by the modulus, and we're using the plastic modulus because we have a class 1 section, multiplied by yield divided by gamma M1, and the answer is 318 kilonewton meters. Again, the use of lookup tables simplifies that process enormously. We have a 457.191.82 UKB in S355 material. It's 6 meters long. We've got a UDL. We do need to know that the C1 value is 1.13 from a source of NCCI, but knowing that, we can extract from the resistance table directly that the lateral torsional buckling resistance is 315 kilonewton meters. I had calculated 318 kilonewton meters, so again, at some intermediate step in the calculation, there is some difference in rounding. Second example then is a simply supported beam. It's got a central point load and it's also got a torsional restraint where that central point load is applied. We have the design actions, 150 kilonewtons as a permanent action and 200 kilonewtons as a variable action. So we can calculate the ultimate loads using expression 610. The ultimate point load is 503 kilonewtons. The maximum bending moment then is WL over 4, or 1006 kilonewton meters, and the maximum shear W over 2 is 252 kilonewtons. So the situation then is that we have two buckling lengths because we have a torsional restraint at mid-span. So we need to make sure that the buckling resistance over that buckling length exceeds 1006 kilonewton meters, and we also need to make sure that the local cross-sectional bending resistance exceeds 1006 kilonewton meters. So first of all, the buckling resistance. We need to establish the C1 factor. So from the concise guide, we have a range of C1 factors. In this case, these are for a linear bending moment diagram, which is the case that we've got. The C1 factor depends on the value of psi, and psi is the ratio of the smaller bending moment divided by the larger bending moment. In this case, psi is 0 divided by the mid-span bending moment, so psi is 0, and C1 therefore is 1.77. The requirements are therefore that the cross-sectional bending resistance is greater than 1006 kilonewton meters and the lateral torsional buckling resistance on 4 meters with C1 equal to 1.77 also is greater than 1006 kilonewton meters. So for a resistance table for a 533 210 122 UKB, we find that the cross-sectional resistance in bending is 1100 kilonewton meters, so that's okay. And for a C1 factor of 1.77 and a buckling length of 4 meters, the lateral torsional buckling resistance is 1060 kilonewton meters, and again that exceeds 1006 kilonewton meters, so that would appear to be okay. The shear resistance from a different lookup table for the same beam is 1450 kilonewtons, which greatly exceeds the design shear of 252 kilonewtons, so that's okay. We do need to check the deflection, and we check the deflection using the characteristic combination of actions, but without including the permanent actions. So therefore the deflection is calculated based on the unfactored variable action. We calculate the deflection as 13.4 millimeters. The limit is taken from the table in the UK National Annex. In this case, we will take the more onerous limit of span divided by 360. The limit therefore is 22 millimeters. Our actual deflection is 13.4, and therefore the deflection check has been satisfied. Moving on again to members subject to both compression and bending. There are two approaches given in the Eurocode, the so-called general method, which will not be used in the UK, and the interaction method. The interaction method involves the verification using two expressions, expression 661 and expression 662. These expressions contain the axial load divided by an axial resistance. In the top expression, 661, it's the major axis flexural buckling resistance. In 662, it's the minor axis flexural buckling resistance. The second term is the applied major axis moment divided by the lateral torsional buckling resistance, and the third term is the minor axis applied moment divided by the cross-sectional resistance in the minor axis. The final part of these expressions are the interaction factors, or the K factors, and they comprise elements which address the shape of the bending moment diagram and the influence of the axial load. So the process then is to classify the cross-section, to check the cross-sectional resistance, even though we know in fact that we're likely to have a buckling problem. It's likely that the buckling checks will be critical. Then we would determine the flexural buckling resistance about both axes. We then calculate the lateral torsional buckling resistance. We then need to establish the K factors, the interaction factors, and that will involve us considering the shape of the bending moment diagram. And then finally, we can verify the section using expressions 661 and 662. So a numerical example. It is a universal column section, a 203 UKC 46. It's in S355 steel and it's 5 meters long. It has a modest axial load of 590 kilonewtons. It has a bending moment of 30 kilonewton meters about the major axis. It's pinned at the bottom. And about the minor axis, a very small bending moment of 2 kilonewton meters, which again is pinned at the bottom of this particular section. So first of all then, we need to classify. And if we consider moment resistance, we need to check whether the section is at least class 2. Because if the section is class 1 or class 2, we would use the plastic modulus. If the section is class 3, we would use the elastic modulus. For the flexural buckling resistance, the test is, are we at least class 3? Because if we are, we would use the gross cross-sectional area, and if not, we would use the effective cross-sectional area. So for elements subject both to bending on compression, and here we are considering the web, highlighted is the limit for a class 2 section. And you'll see that this depends on the value of alpha. We have an expression for alpha, which depends on the applied axial load and the resistance of the web. So substituting the applied axial load, 590 kilonewtons, and the dimensions and the yield strength for the web, alpha is determined to be 1.21. Our limiting C over T ratio depends on the value of alpha. Is it greater or less than 0.5? Our value clearly is greater than 0.5, so we can calculate C over T in this case as 25.1. From section property tables, the actual C over T ratio for the web is 22.3, which is less than the limit of 25.1. So the web is at least class 2. For the flange, the class 2 limit is 10 epsilon. The limit is therefore 8.1, and from section property tables, our actual ratio is 8, which is less than the limiting value. So the flange, again, is at least class 2. Because both the flange and the web is at least class 2, then the whole section is at least class 2, and therefore we would use the plastic modulus and the gross area in our subsequent calculations. Classification would be simpler if we used the lookup tables. So the highlighted column shows ratios when at certain levels of axial load our section becomes not class 2 or not class 3. For our particular section, the level of axial load when the section becomes not class 2 is a ratio of 1, which means that for any level of axial load, the section is at least class 2. So the use of the lookup table would have circumnavigated the use of the various sheets in the Eurocode and checking the limits against the actual ratios. We can use this simple lookup table if we wish. We can then go on to check the resistance of the cross-section, and to do that in this case, I'm again going to use a lookup table. The moment resistance depends on N, which is the ratio of the applied axial load divided by the cross-sectional resistance. The cross-sectional resistance is given us in the table, which in this case is 2080 kilonewtons. Our applied axial load is 590 kilonewtons, so the ratio N is therefore 0.28. So selecting the ratio of 0.3, we can see that the major axis resistance is 140 kilonewton meters and the minor axis resistance is 81.4 kilonewton meters. Both of those comfortably exceed the applied moments, and therefore the cross-sectional resistance in bending is fine. We can then go on to check the buckling resistance. We could determine the buckling resistance using lookup tables. That would be easy and straightforward, but later, when we calculate the interaction factors, the K factors, we will need the intermediate values of lambda bar in the major axis and the minor axis. So therefore, if we are going to verify using expressions 661 and 662, we do need to calculate these intermediate values. So first of all, in the major axis, I'm going to establish the non-dimensional slenderness. So the buckling length divided by the radius of gyration, 56.7. The factor lambda 1 for the grade of steel is 76.4. So lambda bar, the non-dimensional slenderness, is L over I divided by lambda 1 is 0.74. We then need to choose a buckling curve. We have a rolled section. The H over B ratio for a universal column is less than 1.2. The thickness of the flange is less than 100 millimeters. We're interested at the moment in the major axis buckling, so the buckling curve is curve B. Using a lookup table, we know we're interested in curve B. We know the value of lambda bar, and therefore the reduction factor chi we can establish as 0.76. So we can then calculate the flexural buckling resistance about the major axis, 0.76, multiplied by the area, which we've taken from section property tables, multiplied by the yield strength, divided by gamma M1. And the resistance is 1583 kilonewtons. We can do the same thing in the minor axis. In this case, the radius of gyration in the minor axis is 51.3 millimeters. Lambda 1 is still 76.4, so the non-dimensional slenderness lambda bar is calculated at 1.28. We need to select the buckling curve, so it's still a rolled section. H over B is still less than 1.2. Now, of course, we're interested in the minor axis, so we want to choose curve C. So with the value of lambda bar as 1.28 and curve C, we can use a convenient lookup table, in this case taken again from the concise guide. With a little bit of interpolation, we can extract chi as 0.4. So the resistance then in the minor axis, chi times area times yield divided by gamma M1, and the resistance is 834 kilonewtons. Moving on to the lateral torsional buckling resistance, in this case we have a triangular bending moment diagram, and from an NCCI source we would establish that the value of C1 is 1.77. So we can calculate the elastic critical buckling moment. Notice the use of the 1.77 factor there. The answer is 346 kilonewton meters. Then we can calculate the non-dimensional slenderness lambda bar LT. Because we know that the section is at least class 2, we're using the plastic modulus, and the value of lambda bar LT is calculated to be 0.71. We then need to choose a curve. So we would turn to the UK National Annex. We know we have a rolled section. We need to determine the H over B ratio. In this case it's a universal column, so H over B is approximately 1. It's certainly less than 2, and therefore we would select buckling curve B. Again, we can use a convenient lookup table. So for H over B less than 2, and with a little bit of interpolation, we can extract the value of the reduction factor KLT as 0.86. It will be worthwhile in this case to calculate a modified value of KLT, because as C1 increases, the influence of the F factor becomes more and more beneficial. So the F factor depends on Kc, which is associated with the shape of the bending moment diagram. We know that Kc is defined in the UK National Annex as 1 over the root of C1. C1 for a triangular bending moment diagram is 1.77, so in this case Kc is 0.75. We can then substitute to calculate F, and in this case the value of F is computed to be 0.88. So in this particular instance, calculating a modified value of KLT is beneficial, because KLT mod is now calculated to be 0.97. KLT without that modification was only 0.86, so we will have increased the resistance considerably. The lateral torsional buckling resistance is therefore 0.987 multiplied by the modulus, again it's the plastic modulus, multiplied by yield, divided by gamma M1, and the resistance is calculated as 171 kilonewton meters. We could have established those resistances from lookup tables, but remember, in fact we do need the intermediate values, but nevertheless it's a useful check. So here is our 203 UC46, there is the buckling length of 5 meters. The figures according to the resistance tables are 1580 and 832, and according to my calculations 1583 and 834, so some reassurance that I've calculated the correct resistances. For lateral torsional buckling, it's a triangular bending moment diagram, so C1 is 1.77, the buckling length is 5 meters, the given resistance is 174 kilonewton meters, and I had calculated 171. So some rounding differences somewhere, but reassurance that the figure is almost the same. So then we can determine the interaction factors, or the K factors. These will be taken, because we're doing a manual calculation, from Annex B. So the K factors involve two components. One is the C factor, and the C factor adjusts for the shape of the bending moment diagram. And then there is an amplifier, which allows for the effect of the axial load. So first of all, the C factors come from table B3 of the Eurocode. In our particular example, we have a linear bending moment diagram, so we only need to calculate psi, and psi is the ratio of the smaller bending moment divided by the larger bending moment. In both directions, psi in our example is 0. So over on the right hand side, the value of CMY, CMZ and CMLT is always going to be 0.6 plus 0.4 times 0, which is of course 0.6. So the three values are all the same, CMY, CMLT and CMZ, in each case 0.6. So then we can start to establish the interaction factors. So here are interaction factors. We are over on the right hand side for the first of these factors, KYY. We are on the right hand side because we have a class 1 or a class 2 section. So all we need to do is substitute carefully everything we know into these expressions. So we do that. In this particular instance, we are to take the lowest of the two values that we calculate. So KYY is 0.72. So that's the mathematical approach. We can calculate the same value using a graphical approach. So looking at one of the figures from the concise guide, here is that very same factor KYY plotted for various values of lambda bar y. So lambda bar y, according to our calculations, was 0.74. So that's the position established on the figure. Over on the right hand side, we've got ratios of the applied axial load divided by the major axis flexural resistance. So the applied axial load was 590 kilonewtons, the major axis flexural resistance was 1583, so the ratio between them two is computed to be 0.38. So over on the right hand side we can guesstimate where 0.38 is, and therefore draw an appropriate line for this ratio at 0.38. The intersection with the value of lambda bar y, we can then look across to the left, and the ratio kyy divided by cmy, according to this figure, is 1.2. We know then what cmy is, it's 0.6, so therefore we can establish that kyy is 1.2 times 0.6, which is 0.72, which is conveniently the same as we calculated previously. My observation is that in fact the maths is probably easier. My recommendation is, if you're doing this a number of times, I recommend that you put Annex B into a spreadsheet. Here is the next factor, kzz, so it's a similar variation on a theme. We substitute all the numbers that we know. In this case, again, we're looking for the smallest value, so kzz in this particular instance is 1.19. Kzy, similar sort of process. In this case, we're looking for the larger of the two values, so kzy is 0.8. And finally, the fourth factor, kyz, is 0.6 times kzz, so a very easy calculation, and we compute that to be 0.71. So now, having established the various resistances and having established the interaction factors, we can now verify this section using expression 661 and 662. So here is expression 661. We can substitute everything we know, and the utilisation is calculated to be 0.52. We can do the same thing for expression 662, and the utilisation is computed to be, in this case, 0.88. And we would therefore conclude that the column is satisfactory because both of those utilisations are less than 1. We have used the coefficients extracted from Annex B because they are more straightforward than those that we extract from Annex A. If you're going to use either, I recommend that you put them into a spreadsheet. If we compare and contrast the results that we would get from Annex A and Annex B, you'll notice that according to expression 662, the utilisations are the same, but according to expression 661, the utilisations are quite different. It is not uncommon to find that both of those utilisation ratios are different, quite different, between Annex B and Annex A, so don't be surprised by that. If we thought the full methodology of 661 and 662 was complicated, then there is a simplified approach which is available to us, and that was presented in the iStructE journal back in November 2008. And this is a simplified approach because instead of the interaction factors, the K factors, these are replaced simply with C factors, or a value of 0.78. And the C factors merely address the shape of the bending moment diagram. The penalty of using this simplified approach is that the utilisation is now no longer unity, but rather less than 1.0. If we substitute the values that we've calculated into this simplified approach, it would appear that the column fails. So it demonstrates that the simplified approach, though it is easier, is a little bit conservative. Finally then, to consider the very common case of columns in simple construction. Columns in simple construction are where we design the member for nominal moments, and the nominal moments are produced from assuming that the beam end reactions are applied 100 millimeters away from the face of the column. Any out of balance moments are then distributed into the column above that level and below that level. This is a process which will be familiar to many designers. From the Access Steel resource, there is an NCCI which provides a simplified interaction expression. So there are no k factors in this particular expression. There is simply a 1.5 multiplier on the third and final term. So in the first term, we need to calculate the minimum flexural buckling resistance. In the middle term, it's the major axis moment divided by the lateral torsional buckling resistance, and the final term is the cross-sectional bending resistance in the minor axis. There are some limitations, and here they are, and as we proceed with a numerical example, we will make sure that we satisfy these limits. In most cases, we will. So here is a numerical example. We're interested in the bottom length of this column. It is a column in simple construction. We have an axial load. In this case, the design axial load is 589 kilonewtons. We have a modest moment in the major axis, and we have a very small moment in the minor axis. But both of those bending moments are linear bending moment diagrams. And we're going to verify a 203 UKC 46 in S355 steel. So considering the limitations before we can use the simplified interaction expression, we've chosen a universal column section, so we've satisfied the first requirement. We need to check the section classification. So again, we're going to use a lookup table. Here are the limits when a section becomes not class 3 and the lower limit when a section becomes not class 2. For our particular member, for any level of axial load, the section is at least class 2. So we're definitely not class 4. The bending moment diagrams are linear. We are restrained in both directions at the floor levels. Our final limitation is that because we have a pinned connection at the bottom of this column at the base level, we need to satisfy this ratio that the design axial load divided by the axial resistance in the major axis is less than 0.83. So for a 5 meter length of the column, from a lookup table we can determine that the major axis flexural resistance is 1580 kilonewtons and that the minor axis flexural resistance is 832 kilonewtons. We can therefore calculate the ratio of the design load divided by the major axis resistance as 0.37, which is very definitely less than 0.83. So we've satisfied the final requirement. We do need to establish the lateral torsional buckling resistance, so using a lookup table and appreciating that for a triangular bending moment diagram the value of C1 is 1.77, directly from the table we can establish that the bending moment resistance to lateral torsional buckling is 174 kilonewton meters. The bending resistance in the minor axis we can also extract from the table as 81.9 kilonewton meters. Therefore, we've determined everything we need to know to substitute in this interaction expression, and we determine then that the utilization is 0.78, which is less than 1, and therefore this column is satisfactory. Having demonstrated then a number of numerical examples, it's valuable to point out that there are a number of resources available to designers, many of which have worked examples. So the concise Eurocode guide has been referred to several times during this presentation. That contains the lookup tables for the reduction factors chi and chi-LT. There are a number of publications containing worked examples, so for open sections, for hollow sections, and worked examples for students. There is the Blue Book, which I've used a number of times to extract very simply the member resistances. And then there are a whole range of additional publications, many of which contain numerical worked examples. So my observations are that with a little bit of familiarity, the calculation process becomes straightforward. Often we don't work through the clauses that we find in the Eurocode, but we would tend to use software, or we would use the lookup tables that we find in the Blue Book, and that of course makes the process much simpler. And finally, there are very many support resources available to designers. That concludes the worked examples. Thank you for listening.